Okay, let's dive right into this explainer. We're looking at how Microsoft Research is tackling one of the absolute biggest infrastructure crises of our time, and they're doing it using clues that are literally hidden in plain sight. I mean, we constantly hear about the massive energy demands of the modern world, right? But the real mystery is how we safely map and actually upgrade the infrastructure delivering all that power. So today, we're unpacking a really fascinating breakthrough that does exactly that, using entirely open data. To really grasp why this is such a massive deal, we have to look at the current roadblock. Researchers highlight that decisions about where to add new load to the grid are, well, they're gated behind these incredibly lengthy, opaque processes. The grid is already severely stressed by new mega data centers, renewables popping up everywhere, and extreme weather. But fixing it? That's an invisible bottleneck, mainly because realistic, high-level transmission data is highly classified, to protect critical infrastructure. Because of all that red tape, researchers are usually stuck working with what they call toy networks. These are small, synthetic, and honestly pretty unrealistic power grid models with maybe a couple dozen nodes. It means the brilliant engineers trying to design our energy future are essentially forced to do heart surgery using cartoon anatomy charts. They're flying completely blind when they try to test AI or data-driven solutions at any kind of meaningful national scale. So, facing that massive roadblock, Microsoft Research asked a really bold question. Can we meaningfully understand how the U.S. power grid responds to modern stresses using only open data? They wanted to see if they could just bypass all that clearance tape and map the grid realistically without relying on any proprietary or restricted datasets whatsoever. And to pull that off, they built this incredibly clever three-step pipeline. First up, they laid down a geographic skeleton using OpenStreetMap. They basically crowdsourced the physical locations of existing transmission corridors. Second, they layered on open energy stats from the EIA and US Census data to show how electricity is actually produced and consumed. And finally, they ran some seriously complex physics tests to make sure it actually worked. That third step is really the magic key here. It's called the solvability test, or ACOPF, which stands for Alternating Current Optimal Power Flow. This brilliantly illustrates that the models they created aren't just pretty maps to look at. If the network can't mathematically balance power generation and demand while strictly obeying the laws of physics, it gets thrown out. Passing this test proves their open data model is electrically coherent and structurally sound. And just how structurally sound are we talking? Try 21,697. That is the staggering number of buses in the Eastern Interconnection that they modeled entirely from public data. Remember those toy networks of like 20 nodes we talked about earlier? Yeah, this proves the pipeline actually works at a massive continental scale, accurately spanning 36 states. Okay, so let's put this to the test. Before we can even figure out how much new power we need, we have to solve a physical problem. Where can new transmission wires actually fit? By looking at this open source map, we can pinpoint exactly where the grid is physically saturated right now. Out of over 31,000 US transmission corridors, the vast majority are single circuit, meaning, sure, there's some room to add lines. But take a look at those multi-circuit corridors. Some of those are already crammed with up to 10 circuits. You can't just magically wish more wires into existence there. You'd have to buy entirely new, incredibly expensive rights-of-way. So, this map tells us exactly where we have room to grow. But what happens when you look at dense cities? Because you obviously can't just bulldoze a neighborhood to build more traditional transmission towers. To handle those tight urban spaces, planners are increasingly looking at high-temperature superconducting cables, or HTS links. These things are wild. They're super-cooled links with 10 times higher ampacity. Basically, they can inject massive amounts of power straight into urban centers at lower voltages, completely bypassing the absolute nightmare of dense urban permitting. The impact of testing these on the open data grid is just phenomenal. Take the baseline Massachusetts grid. It showed a highly stressed system with overloaded lines and a wholesale energy price of nearly $23 per megawatt hour. But when researchers modeled adding just 2 of these short HTS links near Boston, the results were night and day. Line overloads vanished completely, and the energy price absolutely plummeted by 42%. Now, the absolutely crucial takeaway here is that market price data is purely reactive. Think about it. A transmission line sitting at 95% capacity and one sitting at 50% capacity look entirely identical in market pricing data, right up until that line is full and prices suddenly skyrocket. Physics-based models, on the other hand, expose those invisible margins ahead of time so we can plan safely and proactively. And understanding those invisible margins brings us to the ultimate high-stakes question of the AI era. Where exactly should we plug in the massive new electricity demands of mega data centers? To test this out, researchers used their model to drop a hypothetical 500-megawatt data center into two suburban Maryland locations. Site A is in the Baltimore area, and Site B is in the DC suburbs. These two sites are literally less than 50 miles apart. On paper, they have comparable real estate prices, population densities, the works. To a standard market analyst, they look completely identical. But the open data simulation immediately shatters that assumption. It proved that picking Site A in Baltimore triggers a catastrophic thermal overload on a nearby transmission line, which causes local prices to jump by over 16%. Meanwhile, if you drop that exact same data center into Site B in the DC suburbs, the existing grid just absorbs it safely, keeping all lines well below their limits. So, what does that mean in real-world terms? $80 million. That tiny, seemingly insignificant $2.10 difference in the megawatt-hour price jump, it adds up to a staggering penalty of roughly $80 million per year. That is $80 million of wasted infrastructure costs that ultimately hit everyday ratepayers, all just for choosing the wrong suburb because someone was looking at market prices instead of a physics-based grid model. Zooming out, this brilliantly illustrates the true power of this open data pipeline. By mapping the grid this way, we completely remove those classified bottlenecks. We enable real physics-based testing at a continental scale. It democratizes the playing field so AI and grid researchers around the entire world can innovate. And most importantly, it provides actionable insights before billions of dollars are spent on the wrong infrastructure. Grounding public data in physical reality empowers all of us to proactively upgrade our grid. And honestly, the best part? This massive data set is literally just the foundation. Microsoft Research is already taking this to the next level by using these models to train AI tools like GridSFM. It's a surrogate that can predict full grid operating points and screen for feasibility in mere milliseconds. It is an absolute game changer for speed, and we'll be covering exactly how that works in part 2 of this explainer. For now, though, it leaves us with a truly fascinating question to ponder. If we can use crowdsourced maps and open data to safely unblock the hidden bottlenecks of the massive U.S. power grid today, what other limits can we shatter for the infrastructure of tomorrow? I mean, what other massive, world-changing mysteries are just sitting there, hidden in plain sight, waiting to be mapped? It's an incredible thought. Thanks for joining me on this deep dive, and I'll catch you in the next explainer.